All right, hello. In this screencast, I want to work out derivation of the Clapeyron equation. And so I'm going to derive the Clapeyron equation in a slightly different form than in the textbook. And so I'm going to derive the Clapeyron equation starting with our expression for the differential of dimensionless g, which is different than the text. But this is how we derived it in class together on the whiteboard, because I think working with dimensionless g is a whole heck of a lot easier. And so having already derived our expression for the differential of dimensionless g, you may recall that we had that the differential of g over rt is equal to negative h over rt squared dt plus v over rt dp. All right, and so you can see our screencast where we derive this if you want some further details. So before we get into our derivation, so to say, I just want to play with our differential terms a little bit to simplify this expression. And so the first term I'm going to look at is this differential of t. Okay, so we have negative h over rt squared dt. And so what I'm going to do there is I know that the differential of 1 over t, so if I use quotient rule, that's v u prime, okay, differential of 1 is just 0, minus uv prime, so minus dt over v squared divided by t squared. Okay, so differential of 1 over t is just negative dt over t squared. So this negative t squared dt can be replaced with just the differential of inverse t. And how I'm going to play with the second differential is first, remember equation of state for real fluids is PV is equal to ZRT. So V over RT then is equal to Z over P. So if I take the second term to be then Z over P dP, well, I know that the differential of log P is just equal to 1 over P dP. Okay, cool. So now I can take this expression here, okay, which I have here. So 1 over P dP I can replace with differential of log P. And so I can rewrite our expression for the differential of dimensionless g as the differential of g over rt is equal to h over r d inverse t, then plus z d log p. Okay, I'm going to put the log p in parentheses so I remember that that is my variable in the differential. Okay, cool. So now if I think about my criteria of phase coexistence, so we'll forget about vapor-liquid coexistence for here. We'll just think about coexistence in general between two phases. We'll call it phase 1 and phase 2. I know that I'll have, and I should also say we're talking about pure component phase behavior. So I'll have thermal, mechanical, and chemical equilibrium. So in this case, thermal equilibrium is equality of temperatures, mechanical equilibrium is equality of pressures, and chemical equilibrium in this case, for the pure component case, would just be an equality of molar Gibbs free energies. Okay, and so if the molar Gibbs free energy of the two phases are the same, right, it'd be the differential of the difference in those two molar Gibbs free energies is just, going to be equal to 0. It's going to be constant. And so it must be then that the differential of the molar Gibbs free energy in one phase is equal to the differential of the molar Gibbs free energy in the other. And since temperature is constant and the same, I can write it in its dimensionless form. All right, and so as a starting point then, for my two phases of coexistence, we'll call it phase 1 and phase 2, it must be that the differential of the molar Gibbs free energy in, say, phase 1 over RT, and I'm just going to write it as T because the temperature in the two phases I know are the same, okay, is equal to, and well, the molar Gibbs free energies are the same too, but I'm going to put that up there so that when I plug in my relevant expressions, so I know what I'm plugging in. Okay, it's going to be equal to the differential of the dimensionless molar Gibbs free energy of phase 2. And so all I'm going to do now here, okay, is on the left-hand side, I'm going to substitute in here, right, or expand out this differential of dimensionless g for phase 1, and then I'm going to do the same thing on the right side, hand side, for phase 2. Okay, where here is where it's useful to designate phase 1 and phase 2, because while the molar Gibbs free energy, temperature, and pressure of the two phases are the same, enthalpy and compressibility Z are not. Okay, so I'll have that the enthalpy in phase 1 divided by R times the differential of inverse T plus the compressibility Z of phase 1 times the differential of log P is equal to the enthalpy of phase 2 over R differential of inverse T plus the compressibility in phase 2 times the differential of log P. Okay, and so what I'm going to do next is just collect terms. Okay, remember temperature and pressure of the two phases are the same. So maybe let me collect the dt terms over on the left-hand side and the z terms over on the right. Okay, and if I do that, I'll have h1 minus h2. Okay, and I'll just write this as over r d inverse t is equal to, okay, so it should be z2 minus z1, but I'm going to write it as negative z1 minus z2, just so the order of z1 minus z2 is the same on the left-hand side and the right-hand side, d log p. Okay, or finally then, let's divide by the differential of inverse t, and we will get that, okay, h1 minus h2 divided by r times, actually we're going to have a negative sign, negative r times z1 minus z2 is equal to the differential of log p with respect to inverse t. Okay, cool. Now, in this case, phase 1 and phase 2 are arbitrary, but let's assume that phase 1 is our vapor phase, and let's let phase 2 be our liquid phase. Okay, so if that's the case, if I have the difference between vapor and liquid phase, remember we're talking about a system at two-phase coexistence, then that's the same as property change of vaporization. Right? So now I'm talking about vapor-liquid equilibrium, where I've now called phase 1 my vapor and phase 2 my liquid. Okay, it doesn't matter how you label these things, but now I'm going to call phase 1 my vapor, phase 2 my liquid. And so now H1 minus H2 becomes delta H of vaporization. Okay, so I get that negative delta H of vaporization over R delta Z of vaporization is equal to the differential of log P with respect to inverse T. Okay, and with that, you just derived the rigorous Clapeyron equation, right? So this equation is rigorously correct, no assumptions necessary. All right, cool. Okay, so this gets the name of the Clapeyron equation. Okay, and so we can write the Clapeyron equation in several different ways. Okay, the different forms of the Clapeyron equation just come from messing with essentially the form of our differential, right? So one way would be to recast the differential of inverse t in terms of, if you go back to our dimensionless G notes, are actually where we started. Right? I could take the differential of inverse t and rewrite it as negative dt over t squared, plug that in and resimplify if I prefer a differential with respect to t. Okay, but I'm going to keep it with respect to inverse t for now, but it's all the same. Okay. Now, even looking at the simplified equation, we can begin to get some insight in terms of expected phase behavior, expected behavior of our properties at vapor-liquid coexistence. And namely, I guess what I'm trying to refer to is, if I'm thinking about vapor-liquid coexistence, let me also go ahead and, this is actually PSAT, right? Typically think of that as our saturation pressure. But if I look over on the left-hand side here, okay, so enthalpy of vaporization, okay, enthalpy of vaporization is always going to be positive, right? So I know that delta HVAP would be equal to delta UVAP plus P delta VVAP, right? So I know that the molar volume is always going to increase upon vaporization, okay? So this term will always be positive. And I know the internal energy of my vapor phase is always going to be greater than the internal energy of my liquid. So this term will always be positive. So delta H of vaporization then will always be positive. Okay. When I look at delta Z of vaporization, okay, remember delta Z of vaporization would be equal to the compressibility of my vapor phase minus compressibility of my liquid phase. Just to think back to what we've done so far in terms of finding roots of a cubic equation of state. Vapor phase is going to be the root, the largest root. Liquid phase will be the smallest root. Okay, so I know that delta Z of vaporization will also always be greater than 0. Okay, so if delta Z of vaporization is always positive, delta H of vaporization is always positive. Okay, so now I have differential log P with respect to inverse T. Okay, so just looking at this equation, we know then that vapor pressure will increase with respect to temperature. As temperature increases, vapor pressure increases. Cool, all right? And so, it's something that likely you just know, but now in theory we just proved it from our Clapeyron equation. And it all started from the combined statement of the first and second law. Okay, so using just this expression here, we're able to show that vapor pressure increases with respect to temperature. Okay, so vapor pressure increases with increasing temperature. And we'll make some simplifications to make this even more clear. But one big thing that this Clapeyron equation suggests is that log PSAT should scale with respect to inverse T, right? So if I'm thinking about finite difference, okay, so I'm looking at really, really, really small changes in temperature. So for small changes in temperature or small changes in inverse T, okay, if I take delta H vap and delta Z vap to be constant over that small temperature range, right, that would suggest that log P should scale with inverse T over that small range. And so this already gives us insight then in terms of how I might think about plotting my vapor pressure data, and then also how I might think about interpolating and extrapolating from a finite data set. Okay? And so there's some examples of that in the PowerPoint notes that we'll look at in class and are posted online. But let's make a couple more assumptions to get to what's called the Clausius-Clapeyron equation. Okay? And so the assumptions we'll make in the Clausius-Clapeyron equation will be, 1, okay, we're going to assume delta Z of vaporization is approximately equal to 1. Okay? So what does that mean? Well, so we said that delta Z of vaporization is going to be equal to Z vapor minus Z liquid. Okay? So what this really boils down to is, and let me go further and say, remember, Z is equal to PV over RT, where if I'm at phase coexistence, okay, P and my two phases are the same as our RT, all right? What's going to be different in the two phases is just molar volume, okay? So we can think of this two ways, okay? So one would be, I could take this expression, and I could write this as P over RT times V vapor minus V liquid, okay? So if I assume that, 1, the molar volume of my vapor phase is much greater than the molar volume of my liquid, right? And so in doing so, we assume that VV minus VL is approximately just equal to VV, right? That molar volume of the liquid is just negligible. Okay? So if we assume that, so that the molar volume of my vapor is huge compared to the molar volume of my liquid, so the molar volume of my liquid is negligible. And then 2, if we assume that the vapor phase is an ideal gas. So if you assume that the vapor phase is an ideal gas, what that does then is P over RT, P over, okay, let me see if I can get this right. That means P over RT times V, which is equal to Z, is equal to 1. Okay, so if we make those two assumptions, then we get delta Z of vaporization is just equal to 1. Okay. And then the second assumption, so if I go to the next piece of paper, the second assumption made in the Clapeyron equation is that delta H of vaporization is constant. Okay, so if you kind of think about these assumptions, where the kind of idea or motivation behind assumption 1 comes from is if we're at low pressures. Okay, so if we're at low pressures, then this is reasonable or seems reasonable. Okay, and 2, delta H of vaporization is not constant. So if you just plug into a Watson's equation, essentially you have this power law relationship or exponential relationship between vapor pressure and temperature, and so it's not really constant. It's only constant over narrow temperature ranges. Okay, but in doing so, so if we start with just assumption 1, all right, if I go with assumption 1, that gets me now to negative delta H of vaporization over R. Okay, so I'm taking negative delta H of vaporization over R delta Z. Delta Z now is 1. So this is equal to the differential of log PSAT, with respect to inverse T. So if I assume that vapor pressure is constant, right, it doesn't change this at all. Okay, the significance of it, though, is now if I want to try and get an expression for pressure, vapor pressure as a function of T, with delta H vaporization being constant, independent of temperature, I can just separate and integrate. So if I separate and integrate, so I'm going to have negative delta H of vaporization over R, d inverse T, is equal to the differential of log PSAT. So if I take this left-hand side and I integrate from, let's call it T naught, our reference state, to our temperature of interest. Right-hand side, we integrate from reference state, say P naught, to a pressure of interest. Looking at this left-hand side, this is just constant, so it can come out of the integral, and I get negative delta H of vaporization over R. And now integral of inverse T is equal to, what is that? Log ratio of temperatures, right? Well, no. It's just the integral of the differential of 1 over T, so this is just 1 over T minus 1 over T naught. Sorry. And that's going to be equal to, left-hand side is integral of the differential of log PSAT, so that's just log PSAT minus log P naught sat. Cool. So all I'm going to do is distribute and collect terms. So over here then, I'm going to have negative delta H of vaporization over R times inverse T minus, so now it'll be plus delta H of vaporization over R times 1 over T naught is equal to log PSAT minus log P naught sat. So I get then, I'm actually going to kind of flip these sides. The log PSAT is equal to, let's write this first positive, delta H of vaporization over R T naught plus log P naught sat minus delta H of vaporization over R, I'm going to write this times 1 over T. And so if I do that, or why I'm going to do it, is we assume delta H of vaporization is constant, R is constant, T naught would be my reference temperature, P naught would be my reference pressure. So this whole grouping is just a constant, right? Let me call it A. Then if I look over here, delta H of vaporization, again, we assumed is constant. R is constant. So this whole group then just becomes a constant, call it B. And we get that log PSAT is equal to A minus B over T. So, in making these two assumptions, that enthalpy of vaporization is constant and delta Z of vaporization is equal to 1, we can get a final expression of the form log psat is equal to a minus b over t. So this suggests that log psat scales linearly with inverse t. So if I were to plot log psat versus inverse t, the result would be a straight line. Okay. Slope would be negative b, where negative b is equivalent to negative delta H of vaporization over R. So b is equal to delta H of vaporization over R. And then a is equal to, my y-axis intercept is equal to this term right here. Okay. So this is typically called or referred to as our Clausius-Clapeyron equation. And kind of the significance of this is, think back of the Antoine equation as you would have used it extensively in your mass and energy balance, right? Antoine equation, oftentimes vapor pressure is log base 10, but natural log is one and the same. It's just a change of a base equation or a change of base expression. But Antoine equation would take the form of log psat is equal to a minus b over t plus c, right? So the origin of the Antoine equation comes from Clausius-Clapeyron equation. Antoine equation works well for correlating data over narrow temperature ranges. Right? Antoine equation with the addition of this parameter c is applicable or able to correlate over a much wider temperature range. Okay, cool. So that's our notes on Clapeyron equation and Clausius-Clapeyron equation. You can have a look at our screencasts for more details and discussion of those terms.